Michaela. That was great. Okay, now our next speaker is Abbas Askar, who's going to carry on from or evolve from what was just shown. So this is the dynamical formation of compact object binaries.
Okay, good afternoon, everyone. It's really a pleasure to be here, and thank you for the organizers for having me here to talk about this topic. I'm Abbas Askar. I'm a postdoctoral fellow at the Copernicus Astronomical Center of the Polish Academy of Sciences in Warsaw, where I'm a PI of the grant called Black Hole Growth, where we are trying to understand different ways in which black holes can grow in dense star clusters. So, quick recap, you've seen this figure a few times. We know of announced about 80 merging binary black holes in the LIGO Virgo Kagra detections, and a couple of binary neutron stars and a few black hole neutron stars. And really the key question is, what is the astrophysical origin of these merging black holes? And just to also remind you that each observable also informs us about the masses of these merging compact objects, something known as the effective spin, which describes the spins and their orientations with respect to the plane of the orbit, and possibly eccentricity, but that's complicated, and merger rates and distances and localization as extrinsic properties. So what is the astrophysical origin of these black holes? Michaela already gave you a very nice explanation of the isolated binary evolution channel. Essentially, you need two compact objects to come really close together. So binary evolution processes such as mass transfer and common envelope evolution, which Michaela described, they really help in bringing together binaries and making them merge within the age of the universe. On the other side, there are also these dynamical channels, and then also channels which operate in gaseous environments. And this diagram might be misleading. It might make you think that these dynamical channels are immune from all the uncertainties which Michaela described, but that's not actually true. Yes, so for these channels, they provide complementary ways to form these binary black holes, and there's some processes there which can help bring together binaries and merge them within the age of the universe. But some of these uncertainties which affect isolated binary evolution can also affect dynamical channels. And of course, you can also have non-astrophysical origins for these merging binary black holes. But for the purpose of this talk, I will be focusing on the dynamical formation. And by dynamical formation, I mainly mean formation in dense stellar environments. So essentially star clusters is what I'll be focusing on. So star clusters, they come in different shapes and sizes and ages. So you have open clusters and young massive clusters. So these typically tend to be young. The young massive clusters one are less than 100 million years. Open clusters can be a few million years to up to a few billion years old. Their masses range from a few hundred to up to 10 to the 5 solar masses, and their radii are usually compact with central densities ranging from 10 to 3 to 10 to 10 to the 3 solar masses per cubic parsec and larger. All globular clusters, these are also very interesting sites and very good laboratories for stellar dynamics, and I'll talk a bit more about them. Their typical masses are between 10 to the 4 to 10 to the 6 solar masses, and their central densities can be of the order of 10 to the 5 solar masses per cubic parsec. And then you have nuclear star clusters. These are also, as the name suggests, these are located in the center of galaxies. So these almost 80% of all galaxies with stellar masses of about 10 to the 9 to 10 to the 11 solar masses have a nuclear star cluster at the center, which has a typical radius of a few parsec, and central densities in there can be as high as up to 10 to the 7 solar masses per cubic parsec. And often these nuclear star clusters, they coexist with a supermassive black hole, and that can also play an interesting role in the dynamics of forming compact object binaries. So in the bottom here are local merger rate densities for binary black holes that come from these different dynamical sites. And there's really a lot of work that has gone into deriving these rates and understanding the processes which go on. So by no means this is an exhaustive list here, but in these papers you can really find the theory as well as figuring out the rates for how to for these systems in terms of producing binary black holes. So most of the talk will focus on how to get binary black holes to assemble within these star clusters. Here, I just wanted to give you an idea about the central density of these such systems. So the nearest star to the sun is the Alpha Centauri star system, which is at a distance of about 1.3 parsec. Now imagine if the sun was at the center of a nuclear star cluster or a dense globular clusters, this whole volume would be packed with stars. And if you ever wondered what the night sky would look like if you were at the center of a star cluster, well, it will look like something like this. This is what the night sky will look like if you were at the center of the globular cluster 47 Tuc. It's based on simulations. So the stars would be literally be packed with stars. And these sort of clusters, you see them, we observe about 200 or so in the Milky Way galaxy, but their specific frequency increases with the mass of the host galaxy. So giant elliptical galaxies can have up to tens of thousands of these clusters around them. So a quick primer on dynamical evolution of star clusters. So in these star clusters, you have many stars and their mutual gravity determines how their orbits evolve and how the system evolves as a collective evolution. It's collective evolution. So essentially what you have in these clusters is that you can have stars, these undergo which nudge their orbits and change them over time. And this process is known as two-body relaxation. And this is what drives the dynamical evolution of star clusters. And what's interesting is that the timescale for this process is typically less than the age of these systems. So unlike galaxies where the relaxation time is typically larger than their age, in these star clusters, these two-body relaxation really has a strong effect on how they evolve. And the consequence of having self-gravitating systems is that you have a negative heat capacity. So in these clusters, if you take out energy, they get hotter. And essentially what's happening is that you have stellar interactions going on in the core, which heat stars, so you send stars out into the halo. And as a result, the core of these clusters, it contracts, and then you speed up interactions, and hence you increase the temperature of the system. And as I show you, this can be quite important from the point of view of forming compact object binaries. So some of the consequences of two-body relaxation is that you can get evaporations. Star can exchange energies, which can lead to them being unbound. You could get mass segregation, where you can have the two-body relaxation try to equalize the kinetic energy. So more massive stars, they sink into the center of the cluster. And this drives what is known as this core collapse. So the core can continue collapsing. But core collapse is halted through dynamical processes as well. And this is mainly in the form of binary heating. So you can have three stars come together, form a binary system. And this binary system can then exchange its internal energy with surrounding stars and become harder. And as a result of doing that exchange of energy, it can basically prevent the cluster from collapsing further. Binaries can play a very important role in the evolution of these dense stellar systems, and interactions of binaries with other stars can also be extremely important. They can change the membership and properties, and if you can get binary components to come close in together, they can then spiral and merge before they can heat the cluster. So essentially, this is what you have going on in the star clusters. And now if you want to realistically model these systems, you need to start out with some initial models, some ingredients. So essentially, you start off with an initial mass function. Then you distribute your stars according to some positions and velocities initial ones, which are derived from some equilibrium models in the way it's usually done. And then you can have an initial binary fraction in there as well, which is also very uncertain. But this is very important. Having primordial binaries from the very beginning can play an important role in the way the cluster evolves. And in terms of the physics that you need to simulate a realistic star cluster, you need the treatment for the gravitational dynamics. You need stellar and binary evolution. And then you also need the treatment of the galactic field, as these clusters are not evolving in isolation. They're within a host galaxy. They're also losing stars because of that. So you need to take all that into account. So it's a lot of discrepancies in both length scales and time scales. And also this makes the problem very challenging because it has to be multidisciplinary. You have to take into account a lot of different processes occurring at different time scales. So the way you go around simulating the evolution of these star clusters is through numerical simulation codes. And one way of doing that is these direct summation codes. So in order to treat gravity in these simulations, you essentially have to calculate each force one particle exerts on the other, on all others in the system, and then move that system forward in time. And this is the main architecture of these direct n-body codes, such as these n-body X and these n-body 6 plus GPUs. So then people, this can be extremely time consuming, these simulations. So a lot of acceleration techniques have gone into it, and the use of GPUs has really helped speed up these simulations. But still, to simulate a realistic star cluster with up to 1 million stars, up to the age of the universe, can take easily up to a year, even with GPU acceleration. And then there are some new simulation codes as well, which combine the star cluster evolution with of collisional systems like star clusters with some techniques from collisionless n-body codes, such as PTAR. And these can give you a map. You can do simulations which would take you years with direct n-body, can take up to months with this. Another approach, which I've worked on a lot, is the Monte Carlo method. So this method was devised by the French mathematician Michael Hennon. And there are two codes currently in use which are based on this method. So this is the CMC code developed at Northwestern over a long time, and the other one called MOCA, with which I work with. And these essentially the n-body method uses the direct summation, the particle based approach of n-body, and combines it with a statistical treatment for relaxation, which really allows you to speed things up. But of course, there are some, it comes at a cost. So it's limited to spherically symmetric systems, such as old globular clusters. And then the idea is that you mimic relaxation by changing energy and angular momentum over larger time steps than the ones that you need for that the ones which direct n-body codes can resolve. And both these families of codes, the ones currently in use, they also employ prescriptions for treating binary and stellar evolution, as well as treatment for the galactic field. More recently, there's also been development of fast semi-analytic and population synthesis type codes, which are more oriented towards gravitational wave system, producing gravitational wave systems. And they use more like analytic prescriptions, and they're calibrated against results of direct n-body simulations as well as Monte Carlo simulations. So this is essentially the framework that you need to simulate star clusters. And based on these simulations, I'll be trying to answer some of these questions here. So one of the key questions is, what happens to black holes in globular clusters? Do they receive large kicks when they are formed, and what fraction can be retained? Then what are the dynamical processes that actually lead to the formation of binary black holes that we are detecting with ground-based detectors? And what is their contribution to the merger rate? And lastly, could intermediate mass black holes from a few hundred solar masses to up to a few thousand solar masses form in these dense environments? So black hole formation, like as Michaela already mentioned in her talk, there are some uncertainties there which can be important from the dynamical point of view as well. So we expect stars which are typically above 20 solar masses, give or take, to evolve into black holes. So given a typical initial mass function, you would expect about 2 in every 1,000 stars to become a black hole. And then whether you keep them in the cluster depends on two things: what kind of natal kicks they received at birth, and what is the escape velocity of the star cluster in which they are born, right? So there's some uncertainty whether stars actually directly collapse or they undergo core collapse supernovae, and this can have a consequence on the natal kicks that they receive. So with core collapse supernovae, which form neutron stars, we know from the distribution of neutron stars in the galaxy and the distribution of their proper motions that they're moving quite fast. And this has led people to infer that they're born with high natal kicks, which can be up to a few hundred to up to 1,000 kilometers per second. The other idea is that if some fraction of your black holes are forming through direct collapse, in which you do not have any mass ejection, then it's possible that the black holes are born with low kicks. And in that case, that can have the kicks can be a few kilometers per second or not there at all. And this can really help you retain them in dense environments. And if the evolution of the black hole progenitor really depends on all these uncertain things such as winds and their dependence on metallicity and the final supernova model, this can really affect the black holes you produce and what kind of masses that they end up with. So here's just to illustrate to you an example. Here are two simulations of a star clusters with 700,000 stars initially, and an initial binary fraction of 10% at a metallicity, which is about 5% of solar. And this velocity, this cluster has an initial escape velocity of about 33 kilometers per second. And then we consider two cases, one where we give the black holes the same kicks as neutron stars when they're born, and then the other case where we assume that the kicks are, the black hole masses are higher, and you can also get direct collapse of black holes of about 30 solar masses. And then you find that, yeah, in the case where you decrease the kick, you can retain up to about 60% of the black holes. But if you give them the same kicks as neutron stars, then you can have retention fractions as low as a few percent. So this is really one of the uncertain things that you have to be careful about. There are some observations of stellar mass black holes in dense star clusters like globular clusters. So for many years, we knew of accreting black holes in binary systems through X-ray and radio observations. But more recently, there have been some detections of black hole radial velocity measurements, mainly through MUSE, in which you can see star going around an invisible companion, and then you can infer the minimum mass, and the minimum mass of the invisible companions is consistent with stellar mass black holes. So this one cluster, NGC 3201, has at least 3 stellar mass black holes in them, and there could be many more single black holes in there as well. So now coming to the processes which actually form the binary black holes that we might be observing. So as I mentioned earlier, the most massive objects, in the cluster, as they move through the sea of low mass stars, they create a wake of low mass stars behind them, which slows them down. And this makes them sink to the center of the cluster, where they can then interact with each other and also with surrounding stars. So you can get these exchange interactions. So for example, you have a black hole and a star in a binary, another black hole will come, and it's more energetically favorable for the black hole to take the star's place, and then you can have a binary form in this way. Another important process is the hardening of binaries. So if you have existing binaries, they can undergo these flyby encounters with other stars, and in that case, the encountering star extracts energy out of this binary, and the binary tightens as a result of that. So I prepared a simulation here for you. It's a 3-body encounter of a binary black hole with a third black hole. So you have two 30 solar mass black holes in a binary, which has a separation of about 0.5 AU and an eccentricity of 0.33. And the time it would take such a binary to merge within, due to gravitational wave radiation, is of the order of about 246 billion years. So the timescale for gravitational wave merger, it depends on the separation of the binary as well as its eccentricity. So after this encounter, in which the binary encounters a single black hole, you get what is known as this resonant flyby. So you create this state where, so the star comes in this way and the binary comes in this way, and then you get this temporary exchange. But at the end, the two binary components that were originally in the binary find themselves, and the single black hole goes the other way. And as a result of this interaction, you essentially change the properties of the binary. You make it slightly harder, but you make it really more eccentric, and then you can merge it within a fraction of a mega year as compared to the case. So this is really what dynamics can do. Just simple one interaction can really take a binary which would not merge within the age of the universe and make it merge within the age of the universe. And as a result of these encounters, what you can also get is that the binary center of mass can receive a recoil due to the interaction. And this can also eject out binaries from star clusters. So very hard binaries, which would merge within the age of the universe, could also get ejected out of the star clusters. And what we know in the last decade or so of doing these star cluster simulations is that the black hole populations in clusters, it depletes with time. And the rate at which it depletes depends on the properties of the star cluster. So initially dense clusters that start out as being dense and in which dynamics is more important, you get more interaction in them, and then this faster depletes the black holes within them. In less dense clusters, you get fewer interactions, and then there's a slower depletion of black holes. And these black holes, they're playing a very important role in the way the cluster evolves. So they are basically providing the energy to support against core collapse. And then as they get depleted with time, the cluster core can become denser. And it's these dense clusters, which are more efficient at actually forming binary black holes. So some of the work which we did from about 2,000 star cluster models, which spanned a large initial parameter space of initial masses, initial sizes, different metallicities, with and without natal kicks. From about 1,000 of them, we found that there were about 17,000 binaries that would merge within the age of the universe out of a total of about 40,000 binary black holes. About 17,000 were merging outside and about 3,000 were merging inside. The ones merging inside, most of these mergers occur early on in the cluster evolution within the first 500 mega years. But then you also have a tail of these later, of these binary black holes which will merge at later times. And most of those were dynamically formed. So by dynamically formed, I mean that there was either an exchange encounter or dynamics really influenced the way the primordial binary evolved in this way. And here's an illustration of how you can get a binary black hole to form in a star cluster. So you get two single black holes form in the cluster far away from each other. Then in the first 145 million years of the cluster evolution, they undergo numerous various encounters. So this key here is basically each interaction that you see on the left here is basically an encounter with another star. And through this way, this single black holes can enter into binaries, undergo flyby encounters, undergo even mergers in some cases with another star, and eventually they end up in two separate binary system, which has a binary encounter, and the black holes exchange and find into each other, and they form a binary with properties which will allow them to merge within the age of the universe, so within 200 million years from the start of the simulation. So, but this merger will occur outside the cluster. So, but this is an example of the way dynamics can bring together black holes and form them. And based on these same simulations, we also tried to estimate the local merger rate. It's similar to the way it is done for the field. But in order to do this, you need to assume some star formation rate, and particularly star formation rate, which occurs in bound globular clusters, which are similar to the ones we are modeling. So this is, again, very uncertain. Based on present day observations, we know that only a small fraction of a galaxy's stellar mass is locked in these globular clusters, but it's possible that it could have been higher. And this is the sort of chirp mass distribution we can get from our models. But again, this is extremely sensitive to the input physics that you use. So these are some results from completely new models, which use updated stellar evolution and binary evolution prescriptions. But in particular, the maximum stellar mass black hole you can form in these simulations from single stellar evolution is about 45 solar masses. And then this can really affect the chirp mass distribution. And it can also give you these sources with high chirp masses, which I'll talk about shortly. But the main open question here is how much star formation took place in globular clusters. So you have people who try to estimate the rates as a function of redshift. And then really this question of the globular cluster star formation rate becomes a question mark. And at high redshifts, it's possible that a larger fraction of the mass in the universe was in these bound stellar clusters, which could have produced these merging binary black holes. But it's extremely uncertain. And then there's always this interesting question about which dominates, the isolated evolution channel or these dense star clusters. And yeah, this is just an illustration of this. It's a comparison of this binary black hole formation efficiency. So the number of merging binary black holes that you can form divided by the for per million solar mass for different metallicities. And based on these results, at least in which there were many very different prescriptions for the stellar evolution, globular clusters are more efficient across different metallicities at producing binaries that will merge within the age of the universe. So it's possible that binary black hole formation could be more common in these environments, but that their overall formation is rare. And in this work, we try to come up with a way to estimate, based on the cluster properties, how many merging binary black holes they can produce. So this gamma basically takes into account the initial mass of the star cluster, its density, and its primordial binary fraction. And essentially what we find is that the more dense and massive a cluster is, the higher the number of merging binary black holes it produces across data sets coming from different simulations. So there's this correlation that the more dense and massive the cluster initially is, the higher the number of binary black holes it will produce. Another interesting thing is that in these close encounters like the ones I showed you, you can also have a non-negligible probability that the two black holes during these interactions can actually merge. And in particular, if you include post-Newtonian corrections while computing the outcome of these interactions, you can actually find this case that you can get a gravitational wave capture and merger. And in some cases, you could have measurable eccentricities when this binary enters the detectability band. So such a detection would be really interesting. However, it's observationally, it's not easy to disentangle eccentricity from a spin orbit precession. We need better waveforms to be able to do that. But this could be another good evidence for dynamical formation. But such formation can also occur in other places, such as hierarchical triples in the field. And you can also have eccentric mergers take place in binary-binary interactions. And just a quick word on the open clusters and young star clusters. So while in these dense globular clusters, star formation, not a lot of star formation might have taken place, but these young clusters which trace star formation, so wherever a much higher fraction of stars could have been born in them. And then it's possible there that dynamics as well can enhance the rates. And in this work from DiCarlo and collaborators in 2020, they actually showed that at high metallicities, these clusters can be more efficient per solar mass at producing binary black holes than isolated binary evolution calculations shown in gray here. And then you can also have low mass ratio mergers produced in these environments. So this is also an interesting consideration. And I'll just use the last few minutes I have to talk about GW 190521 type events, which Michela also referred to in her talk, in which we see primary masses which are above in this upper mass gap of about 50 to 120 solar masses. It's very interesting how these systems form. And when they were first detected, there was a lot of interest in the dynamical community, because one of the more straightforward ways of growing black holes in star clusters is that you have two black holes which formed from stars merge. So these black holes are first generation, and their merger produces a second generation black hole, which can then pair up with another first generation black hole and merge again. So in that way, you can have stellar mass black holes increase their mass. And there were a lot of papers out about this. But there's one major roadblock into this very simple pathway, which comes in the form of gravitational wave recoil kicks. So as you have, when black holes merge with one another, in the final stages of the in-spiral, the gravitational waves, there's an asymmetry in the emission of the gravitational waves. So the merger product actually conserves linear momentum. And these kicks can be up to a few hundred to a few thousand kilometers per second. And as a result, the merged star is difficult to retain in the dense environment, so it cannot pair up again. So this is a big issue. And the magnitude of this gravitational wave recoil kicks depends on the mass ratio of the merging black holes, their spins, both the magnitude as well as the orientation of the spins. So one possibility is that if these black holes are born with low spins, then when you have this first merger, so in this figure here, you see the magnitude of the gravitational wave recoil kick as a function of mass ratio for two different spin assumptions. So the purple line is that you assume that birth spins are low at 0.1, and these dispersed points are that you sample these spins with values going up to 0.7. So if you really have low spins, then you can actually the gravitational wave recoil kick can still be less than the escape speed of globular clusters, but it becomes difficult to retain them. But you have better chances for retaining them in environments where the escape velocity is higher, such as nuclear star clusters. And the birth spins of black holes are highly uncertain as well. There's some studies suggesting that, yeah, you can have efficient angular momentum transport from core to the envelope in the final stages of the formation of the black hole. And in that case, you can get low birth spins. So the first generation merger, it's possible that you could retain the black hole which forms from that. But that black hole is expected to have a higher spin from the merger of two black holes. So when it merges again with another black hole, it might be difficult to retain that merged black hole in the cluster. So in these set of simulations here, we include these cakes, and then we also give a low birth cake to the stars, to the black holes which form. And essentially then we can, it's possible to have some second generation and first generation mergers, which can be in the mass range of these GW190521 type events. And there are other pathways for growing black holes in dense star clusters. I won't go into too many details because Michele already alluded to this, but you can already, in binary evolution, you can also have mergers between stars, which can then produce black holes, which are in this gap. And if you do this in a dense environment, then you have a massive black hole in there already, which can pair up with another black hole, such as the one illustrated in this history here. So there are these alternative pathways of forming these GW190521 type events through binary evolution mergers within dense environments. Just a few words on the challenges and outlook. Many challenges, we can discuss them later in the discussion section. How accurate and representative are our star cluster models? Initial conditions is a big question mark. They're poorly constrained. Input physics is another whole question mark as well. The predictive power of these numerical simulations, when you make rate estimates, etc., they rely on stacked assumptions. Many things need to be correct in order for our predictions to work. And I think the path forward is trying to anchor our models in observations, but that is also not as straightforward as it seems. But this is definitely things to discuss. And I'll leave you with my conclusions for the end. Thank you so much.
Any questions? Yeah.
So thanks, Abbas, for such a comprehensive overview. And I will ask something that is not in the comprehensive overview, sorry. An additional problem, especially for nuclear star cluster, is that usually models assume them to be monolithic, so to form from coeva stellar population, but the same problem may be also for globular clusters.
Right.
So what are your thoughts about it? How much this approximation can affect the result, and how can we move forward?
I think that's a very valid question. So with regards to nuclear star clusters, there is this tendency to think that they formed all at once, but we know from observations as well that there are two different ways in which they form. Probably part of them form in situ, and then merging star clusters can also contribute to their growth. And then this can really affect for what we infer about their escape velocities, for instance, right? So it's not necessary. What we see today was the escape velocity earlier on as well. Same is for the structures that we assume for globular clusters. Things can change a lot if, for example, coming together, bringing together their massive stars, and then you can already have dynamics and binary evolution going on within these filaments that are coming in and forming the globular cluster. So those are definitely things that need to be modeled better. And then there are also big concerns then about, well, how many compact objects can be retained in such when you have such non-monolithic formation of a star cluster. So I think we really need to go back and look at the initial conditions of these models, how close we are to modeling them. And this assumption that everything starts at zero-age main sequence already with this structure, like is predominantly done, really has to be reconsidered, I think, or it has to be done more accurately.
Thank you for the nice talk. It went a bit fast for me. Can you
Mhm.
repeat again? So I'm interested in these upper mass gap
Yeah. Sure.
objects. So you were mentioning like with low birth spins,
Yeah.
You can retain them.
Mhm.
Can you explain again like how low does it actually need to be for to retain them in typical environments? Because especially like if you're thinking like second or third generation, then at least you have like angular momentum of binaries already imprinted into the black hole spins, which is necessarily very high. So
Right.
I wonder like what are the constraints?
Yeah, so really, in order to retain the merged product, birth spins really have to be close to zero, because even having birth spins of about 0.1, these can give you, depending on the mass ratio, there's some spread here, but the first merger between the two first generation black holes can give you already recall kicks of a few 50 to 100 kilometers per second, which might be enough to kick you out of a dense globular cluster, which has typical escape speeds of about 50 or 100 kilometers per second. So that is really something you really need extremely low birth spins to have this first merger retained. I think, yeah, it really depends on what the birth spins are. But then there are also these alternative ways in which you can bypass, for example, the merge. Two stars evolving in a binary. And if one of the stars is in this evolved stage where it still has this envelope around it and it merges with another star, then there's a possibility of circumventing pair instability supernovae and forming a black hole which is directly 70 or 80 solar masses. So in that way, that star can then avoid uh, has avoided the recall kick which you would get from the merger of two first generation black holes. So there's a lot of uncertainty there, and there's a lot of better modeling still to be done. Yeah.
Thank you for the talk. You mentioned about the eccentricity.
Mhm.
If we can measure the eccentricity,
Yeah.
how would it help in distinguish between the different models? So what is the importance of measuring the eccentricity? For example, with LISA, we may
Mhm.
be able to measure the eccentricity of some of this
Yeah.
BH system.
Yeah, no, that's going to be really important. The expectation is that through binary evolution, really in the last stages of the inspiral, you would expect everything to have circularized by then. But in such encounters or in triple systems, perhaps, you can really have measurable eccentricity before the merger as well as during the merger. And in some cases, this can cause a modulation in the gravitational wave signal as well, which if observable, then would be perhaps a very strong sign that this is not the isolated binary evolution, but something in which dynamics has played a role. It might not be indicative of clearly star cluster because you can get the same situation in triples or in maybe even gaseous environments, but it would be a very strong indicator that dynamics has played a role in merging this binary. Yeah.
The next question's from Zoom. I think it's Syed. Would you like to put your microphone on and ask your question?
Yeah, hi, can you hear me? Am I audible?
Yeah.
Yeah, I just wanted to ask, like, so if I have, let's say, two globular clusters, one in which the spins, I mean, this is continuation of the previous one, that if the spins are very low, then it means that the eccentricity coming out from that globular cluster, like eccentric orbits, would be less, right? Just to clarify. Because if the natal kicks are high, then these objects like these black holes, they leave the globular cluster, so I won't have chance to retain eccentricity in the orbits. Or
You could still have primordial stars in binaries in which you can have high natal kicks, and then you can end up with a binary which has eccentricity, which has high eccentricity, and then which could evolve in that way. But overall, it's not really a connection between the individual eccentricities, and the spins in that way. So yeah.
Okay.
Yeah.
Okay, thank you.
There's time for another short question if there's something. Yeah, okay. I'll sprint to the back.
Hi, thanks for the nice talk. I was wondering, I mean, there is a lot of third-body interactions in the process that you described. How likely is to get a binary black hole merging with a third body around, let's say, close to the
Yeah, so we've estimated the rates of such captured mergers, and they're a small fraction of the overall rate that we expect from the binaries, which will merge without any third object around. So, but it again depends on many initial things, but this can be up to a few percent, up to 10% of all the mergers coming from the clusters could be the ones where there's a third body around. Yeah,
right.
But third body around in general could be much more frequent. We know now from observations that a large fraction of massive stars are in multiples, so higher order multiples than binaries. So triples in the field could also be numerous. And a lot of people are exploring that as a potential channel of forming gravitational wave sources.
Okay, so let's thank this again, please.
Thank you.